So now we know a little bit about CDF, okay, its definition. And let's move to talking about the properties of the CDF, and that is according to the textbook, chapter 4.10, if you want to get a deeper reading of this, okay? But I will go over the key results here, and many of them will be useful for our practices later. So the first one, okay, is that the probability, okay, of X between A and B, okay, however, is exclusive of A and inclusive of B, okay? If you want to use the CDF expression to get this probability, this equals to FB minus FA, okay? So remember, well, if I'm working with a capital letter X, that's the random variable, FB is probability, right, of X small or equal to B, right? And FA is probability of X small or equal to A, right? So if I take the difference between the two, okay, I'm getting the range of the probability of the range of X between those two. But then in particular, we're excluding the lower bound and including the upper bound, okay? So for any A smaller than B, this result holds. Okay, so keep in mind, okay? Sometimes this can be really handy. Another thing I want to mention is that the probability of X smaller than B does not necessarily equal to the probability of X is smaller or equal to B. Okay, so for example, if the probability, like for the example about the coin flip, okay, we know that any X equals to any B, let me just write in this way earlier, right, is 1 minus P to the power B minus 1, right, times P. Okay, that's, remember, P is the probability of getting ahead, okay? And then B, in this case, will be any value that we're evaluating the random variable for. And the random variable, remember, is the number of flips you need to do until you get your head for the first time. So here, well, depending on the P value, right? Like what the value of P is. If P is neither 0 or 1 in this case, let's just say if it's a fair coin, so P is 0.5, then clearly, right, this X equals to B is going to be a positive number. Okay? So because of that, if we compare probability of X smaller or equal to B to X smaller than B, those two won't be different, won't be the same, right? They will be different because X smaller or equal to B includes the case of X equals to B, whereas the first term over here, X smaller than B, does not include that case where X equals to B. Okay, so another way to put it, let me just say this way, is that the probability of X smaller or equal to B, which is our definition of CDF, is the sum of the X smaller than B plus the probability that X equals to B. Okay, so obviously, depending on whether this is 0 or not, or it's a probability, right? If it's 0, then these two equal. If not, they are not equal to each other. Okay, so this is another good way to think about how we can understand about this particular property. A third thing here is that the CDF, okay, is a non-decreasing function. Okay, non-surprisingly, especially if you're coming from this term. Okay, we know that, well, if A is smaller than B, then if you want to get the probability of X is between A and B, you're taking the difference of the CDF, evaluate at the larger value, minus that evaluated at the smaller value. Okay, so this also actually is telling us that, remember, any probability should be between 0 and 1. Okay, so this difference between the two will always be non-negative. Okay, and because of that, it's not surprising, I just want to say, that if you're looking at X1 smaller than X2 here, notice that we're using a small letter. Okay, so they are the real values. Okay, they're not random variables. But if we evaluate the CDF of this function, okay, at two values, one is smaller than the other, then the CDF gonna be greater for the second one compared to the first one. Okay, so I think this too that we talked about can also let us think a little bit more about why this is true, but also try to get an intuitive understanding of this. One other thing here is that, well, remember X, the small x, the real value is on the real line, okay? So what this also tells us is that if I'm letting my small x, the value that I'm evaluating my CDF, if I let it to go up to infinity, then the limit of the CDF is going to be 1. Okay. In other words, if I'm looking at the probability of x is smaller or equal to infinity, well, I'm including all of the possible cases, right? So the probability, which is the CDF of that cumulative event, is going to be 1. Okay. Similarly, we can do it on the other side. Okay. If I'm looking at my small x approaching to negative infinity, okay, that will be probability 0. The reason is because, well, if I'm looking at the probability of x is greater than the negative infinity, well, we know that because it's on the real line. It has to be like this event has to happen. So it's going to be probability 1. And because of that, if I'm looking at x going up, going down to the negative infinity, I'm looking at the other side of the curve in some sense. So that probability, which is the CDF, will be 0. Okay. So we'll see more examples, but this is a handy result. So I just want you to keep in mind, okay? And the last property here is that fx is right continuous. So this again brings back our experience and knowledge from calculus. Okay, so fx, remember, this is the CDF function. So it is right continuous, meaning that for any decreasing sequence, okay, we have a decreasing sequence, let's just say xn, okay, that converges to x, okay, meaning that it's converging to x, then the limit of going, just keep going for the CDF evaluated at xn, okay, so n goes to infinity. Notice that this is a decreasing function, okay, and that will just become the f of x because xn is converging to x, okay, so that's not surprising, okay, but at the same time, what this is telling us is that, well, if I'm looking at my xn, or like n in this case, okay, is going to infinity, so the probability of, which is the CDF here, okay, notice that here my CDF is being evaluated at x plus 1 over n, okay, but because remember n is going to infinity, and then this term is going to decrease, right, approaching 0 as n goes to infinity, then that will just be the same of that whole thing goes away, right, and then the probability, well, p, probability of x, capital X, the random variable smaller or equal to small x, then that will just be the same of what we understand before as the CDF function itself, okay? But this way of writing it is showing that fx is a right continuous function. So keep those in mind. Like I said, maybe it might sound a little bit complicated to get started, but once we start to see more examples, I'm sure you're gonna see why we're defining this and then showing all of the results early on, because all of them are actually pretty handy whenever you're working on with a particular example. In particular, like I said, CDF actually will be really useful because it tells us everything about a random variable capital X. Okay, so I'm showing you an example from the textbook, okay? And in particular, we're showing you on the x-axis, that's the value that the random variable can take, okay? And the y-axis here is the CDF, okay? So take a moment to think about what this graph is telling us. Okay? This graph is pretty interesting, okay? It's showing us the CDF function for the entire possible space of what random variable x can take. Okay, so one thing we notice, okay, it starts at 0. Okay, fx started at 0 when x is 0, small x is 0 here. Okay, so it's a function going to 1 over 2. Okay, straight line. Okay, up until small x equal to 1. Okay, and then from there on, notice we have a dot over here, and then it's a flat vertical line between 1 and 2. It's always at 2 over 3. Okay, and all of a sudden, once x goes to 3, it becomes a vertical line again. Okay, sorry, x equals to 2. Sorry, it's a vertical line again up to x equals to 3, and it's always at 11 over 12. And then lastly, if it's greater or equal to 3, then it's a vertical line, and just keep going. You stop here, but you can just keep going, and then it's at 1. Okay, so one thing, I guess the first thing we can start to understand this graph is remember fx is a non-decreasing function, okay? So all of the step, like say the straight line, and then all of this, the vertical lines over here, they are showing that fx is a non-decreasing function, right? It's either increasing or staying flat, okay? Again, fx here, the CDF is a cumulative distribution function, okay? We're considering, right, like on the x-axis, we're considering all of the possible values, like say x smaller than 1, small equal to 1, x smaller equal to 2, and it's cumulative, right? So fx, the CDF, is non-decreasing because we're adding more probability as we move along. All right, so that's about this graph. So let's think about some key concepts here, in particular, how to understand this graph beyond just what we are drawing over here. So for example, from this graph, one thing we can know is that if I want to know, let's just say, the probability of x is smaller or equal to 1/2, okay? If I want to do that, well, what is this? This is the probability of x is smaller or equal to 0.5. So this is equivalent, right, to f, capital F, which is the CDF definition of 0.5. Okay? If I want to know that, well, if we go back to the graph over here, right, it is a straight line between 0 and 1. Okay, so in order to evaluate it at 0.5, I pretty much just use 0.5, evaluate it for the expression for this line, which is, well, the height is what? The height is 1/2. This is 1, so we know that the slope is 1/2/1. So the probability of x is smaller or equal to 0.5 is actually 25%. Okay, so you can see that it's pretty handy, right? If I know the CDF of this random variable, I'm able to answer certain questions about certain probability of events. Okay, the first event that we looked at is the probability of x is smaller or equal to 0.5. Let's look at another one. Okay, what about I want to know the probability of x is greater than 2? Okay, so this is not directly CDF yet, right? But we know the complement of that. Okay, so the probability of x is greater than 2 is the complement of the probability of x is smaller or equal to 2. Okay, so we use 1 minus that complement, probability of that complement, and this immediately becomes our CDF function, sorry, evaluate at 2. Okay, so CDF function evaluate at 2, if I go to this graph, well, CDF function evaluate at 2 is 11/12, right? So I use 1 minus 11/12 because I have a 1 minus over here. So the probability of the event that x is greater than 2 is 1/12. Okay, I hope you have found this overall pretty interesting. Let's go to a couple of more. If I want to know the probability of x is smaller than 1, okay, notice that it's smaller, not smaller equal to, okay, so it does not include x equals to 1 per se, and that might be a little bit confusing, okay, because all of the stuff that we have now, okay, maybe like if we answer this question first, let me say, if we're trying to find the probability of the event of x is smaller or equal to 1, this equals to, remember, f1, right? And if I go to the graph, f1 is at 2/3. Okay, and if I now go to x is smaller than 1, okay, it does not include the event of x equals to 1 exactly. So it's going to be everything below this line, okay? And if I look at it, this f, like the p of that is smaller than it, will be exactly at this point 1/2. Okay, so that's why it's 1/2 or 0.5 over there. And lastly, keep that in mind. If I want to know the probability of x equals to 1, then it could be the difference between the two. Okay, it could be the probability of x is smaller or equal to 1 minus the probability of x is smaller than 1. So I take the difference of these two, and then I get 1/6. Okay, this is a pretty substantial and worked out example, as you can see. Okay, so I would definitely encourage you to take the time to redo it for each of the pieces here by yourself to convince yourself that you understand and it does make sense to you that CDF tells us everything about the random variable. If I know about the CDF, I can do a lot of other things about understanding the random variable x, say by understanding or by answering those questions about probabilities of certain events.